All right, welcome back. Let's finally start moving into the hypothesis test. So obviously we've already completed a lot of the components. So we now know how to write the hypothesis, null and alternative. We know how to sketch the distribution with critical values based on the alternative. We know how to interpret the results, so the conclusion, do you reject the null or fail to reject? And we also know how to summarize the problem completely so that we can answer the question as to what can we say about the parameter. The last piece that's missing is how exactly do we determine if our sample evidence provides evidence for the alternative? So we've already said if your sample lands here, you're going to reject the null. So that supports your alternative. But if, for example, you land here, then that's fail to reject 0. Now, the way this actually happens varies. So there's two ways for this to occur, and we're actually going to be using both. The one that we've already seen is you use z-scores. This would be called like a test statistic. So this is the test statistic approach. Or we could do a p-value, and p stands for probability. So this would be test statistic. And then p-value is just a probability. And both of these numbers are given to us by StatCrunch. So we already did a hypothesis test. Okay, yeah, I don't have the outputs, but we can get these numbers pretty easily. So that's why we're going to go ahead and do both. And every hypothesis test is accompanied by a level of significance. In other words, at what level does a sample become significant? So this is alpha. Alpha is always the area and the tails, because you're basically saying if I land in these tails, I have a significant sample mean because it shouldn't have occurred. All right, so let's go ahead and just summarize what we have already seen, and that's the classical approach. So the classical approach essentially says, depending on the alternative, so if the alternative has a not equal to, we already know that that's a two-tailed test, and it's a left-tailed test if there's a less than, greater than, we'll have a right-tailed test. And then what we basically say is we're saying, okay, here is my critical region. This is at the point, this is the point at which samples will become unusual if they land in this blue region. So for a given, so this is for proportions. So for proportions, we can compute the test statistics. So that's going to be called z-test. And z-test is simply the number of standard deviations that your sample lands. So it'll be p hat minus the claim proportion, p. So remember that your null hypothesis has a number, right? So this will be p0, so some known number. And then we're going to go ahead and divide that by the standard error for the sampling. And so that would be p0 times 1 minus p0 all over n. Now, the awesome part is that we don't have to do this by hand. Our z-test, basically our test statistic, is found via StatCrunch. And then we're basically going to go ahead and say, okay, my test statistic, how does that compare? If your test statistic lands in the critical region, then check this out. Z-test is greater than Z sub alpha. So that's if you land here. If you were to land on the left, then Z-test is to the left of negative Z alpha. But the easy way to do this is to just simply take the absolute value. So we're going to go ahead and say, okay, let me take the absolute value of my test statistics. So we'll basically push that guy over here. And taking the absolute value just tells you how far away you are from the center. And we've seen this before. All right, and then we'll compare that to C alpha. So all that this condition right here says is that your distance from 0 is greater than Z critical. So you're landing here. That's what that condition says. You don't have to memorize this. I literally will ask you to draw the distribution every single time and then sketch where your sample has landed. So if you land in the critical region, we know that that's evidence to reject the null hypothesis. And then you can go ahead and interpret. However, if we take a sample and my sample lands, let's say here, then what does that mean? That means that my z test is less than my critical. So z test is closer to 0 than z critical. And so therefore, we're going to go ahead and say we fail to reject. Okay, so you don't have to memorize this condition. It's literally just going to be read off of the distribution. So I don't have any of the stuff memorized. I encourage you not to have it memorized. Just kind of reason through what it's saying. All right, so that's the classical approach using test statistics. This is the way people did statistics for most of the time that it's been around. P-value is a little bit different because it's harder to find the probability. So p-value is also called the modern approach. So this is the classical approach using critical value. P-value would be the modern approach. Because now we have software, so it's very easy to find probabilities. All right, so a p-value is the probability of getting a result as extreme as what you obtained. That a different sample will result in a test statistic at least as extreme as what you got. So the p-value, we're literally going to say, okay, where do you land? Let's say your sample lands here. Can we see that? Let's say your sample lands here. I'm not just interested in the location. What I'm going to do is I'm going to go towards the tail, away from zero, away from the center. If we go away from the center, we're essentially saying, okay, so let's say our sample lands here, and then we're going away. Notice that the probability, that red area, is what's called P, the p-value. So the p-value equals the probability of landing in that red region. In other words, more extreme. So we're just saying, how unusual is the sample? By answering the question, how likely is it that if you were to take a sample again, you would get a value at least as extreme as what you observed? So basically, you'll land over here. So notice if you land close to the middle and then you go more extreme to the tail that you're looking at, you get a big area, which means that this is not unusual. Your sample is not unusual because if you were to take another sample, the probability is very high that your sample would be at least as extreme as your first sample. Okay, so the p-value is a probability of essentially being more extreme. So we're just trying to get a sense of how unusual was this sample. Don't worry about the computation on how to do this. We just know that the p-value is the probability away from the center, basically towards the tail. So if your p-value is, let's say, smaller than the significance level is the area in blue. Notice that the red area is smaller. So therefore, we are saying that my sample is unusual. It is rare. Notice how I also land in the critical region. So that's another way that I know. So because the p-value is less than alpha, I basically have a statistically significant, right? My sample is significant because alpha was saying at what point does a sample become significant? And so therefore, we're going to go ahead and reject the null hypothesis. All right, now what if the p-value is greater than alpha? So what happens if our p-value is greater than alpha? So again, that would happen maybe over here. Your sample would land here, and then you start shading towards the tail, and you realize, oh, my probability of getting another sample at least as extreme as what I first got is pretty high. It's not statistically significant. So your first sample is not statistically significant. Okay. It's not that you're going to get two samples. It's just we're saying from this one sample, how likely is it that you will get another sample basically at least that far away from the center? So if it's greater than, we're going to fail to reject the null hypothesis. And notice how you could have answered that question without even doing the area, because you say, hey, I land here, that's the non-critical region, you're going to fail to reject. So these approaches, they work hand in hand. They have the same conclusion no matter what. All right, so the p-value is actually what is in fashion now because we have technology and it's very easy to find the probability of getting a sample at least as extreme to what we observed. So the smaller the p-value, the stronger the evidence is, right? The more unusual our sample is. And if our sample is unusual according to the null hypothesis, then this is going to be evidence against the null. So all of these are against the null hypothesis. Okay, so for a very small p-value, more precisely, any p-value that's less than 0.05, we're going to say is significant. Obviously, 0.05, that is the level of significance, alpha, and the default is 0.05. So you can see that if your p-value is greater than 0.1, then we're not going to be able to reject the null hypothesis because we're getting something like this. All right, let's go ahead and do one example before we end this short video. Let's suppose that you're running a left-tail test with alpha 0.05. If your sample data is in the blank 5% of a normal curve centered at the claim, then it is quote unquote far away. So let's go ahead and see if we can figure out what goes in that blank. And again, I really want you to learn to visualize this because there is no memorization. It's just simply understanding how samples behave. So I'm running a left-tail test. So that means I have a standard normal curve like this. Left area is 0.05. And if you wanted to, you could actually find this critical value. I'm not going to worry about it. But now they're saying if your sample data is in the something 5% of a normal curve centered at the claim, then it is far away. So when are we quote unquote far away? Well, far away, we're in the tail that we've identified. So we would be in here, right? My sample, I would get a sample proportion that lands here. And so again, this is when the sample data is in the something 5%. So that would be the 5th percentile. So the left 5% of the normal curve centered, then it is far away. Let's suppose that you reject the null. So we're saying, hey, we do actually end up landing here. So that means you reject the null. What is a possible p-value for your sample? So my sample would have a p-value because you rejected the null, then the p-value needs to be smaller than alpha. You're saying my sample is significant to that level that you stated ahead of time. Okay, in other words, your sample is unusual. Shouldn't happen under the null hypothesis. Remember, null hypothesis tells you where this curve is centered at. So the null hypothesis doesn't quite fit my data. Okay, so pick any p-value that's less than 0.05. So the p-value could have been 0.04 or 0.03, 0.02, 0.01. If the p-value is very small, a lot of times you'll read it as p-value is simply less than 0.001. Okay, it doesn't go that far out. It's not as accurate. And that's pretty much it. So these are the two approaches that we have for saying, given our sample, I can use a classical approach using test statistics, or I can use p-value. You will need to do both in this class. Okay. All right. So if you have any questions, please make sure to reach out during office hours or via email. And in our next video, we're going to put all of this together and finally do a complete hypothesis test from start to finish. It's going to be like writing an essay.